All right, today we are going to talk about spring rates of materials real quickly, stress concentrations hopefully as a review, buckling of columns, which is very important when you have axial loaded members. I want to make sure that they don't buckle, which is a form of failure that when we have failure that doesn't deal with the failure of a material or exceeding stresses, just enough stress to cause it to bend out of shape. And then we'll talk about pressure vessels. These are the last concepts of our review. These are all things that you would expect to see on something like a fundamentals of engineering exam, and things that come up in basic machine design and stuff that we need to keep in mind. So this is directly from the book. It's just making the connection of spring rates that we should be pretty familiar with when we think about a normal spring, where we have some force over the deflection, then we define that as the spring rate. There's the same equivalent function going on when we have an applied torque that results in applied rotation of the material, rotational deflection. That would be our angular spring rate in Newton meters per radians. This is just your Newton meters. And then we could multiply this spring rate by a distance, and we could get the force that the spring is applying, or the force that the material is, the stiffness of the force the material is, the torque the material is resisting against an applied torque. When we think about beams, though, we have to just make the connection between the spring rate and the beam, and we do that through the deflection. Okay. And we know what the deflection is. For example, a bar, an axial bar, a bar in axial tension. We know that the deflection, the elongation can be found by from the material properties: applied force, the length, cross-sectional area, and Young's modulus. So then we can get an expression for the stiffness of a bar in axial tension. We can get the stiffness of a bar in pure torsion by just keeping these things in mind, that the spring rate is the applied force or load over the deflection. The deflection in the case of the round bar in pure torsion is given by this equation. Obviously, we have different theta representations for different cross-sectional geometries. So we can find the spring rate for a bar in axial tension is this. Okay, and if we have a beam, then all we have to do is, again, get the deflection equation. In that case, we need to know the loading conditions, so we can look at the loading. In this case, we have a point load at some distance A in a cantilever beam, which will have a moment and a reaction force to resist this load. And we can use our beam equations to get an expression for the deflection. And this is from one of the examples earlier, example 4.5. And so if we can do that, and then we can express the deflection of the beam. In this case, it's at x equals L. Then the spring rate is that force over the displacement, which is 3EI over L cubed. Okay, so this is a useful thing to know in our design, because we can determine what if we find the spring rates of a material, then for a given load, we can get a quick estimate of the deflection. So every material is a spring, all right, because it follows some stress strain curve with some slope. Now, if it's linear, as in the case of many materials, such as many engineering materials, aluminum, steels, etc., then we have these nice relationships here where we can look at the spring rate of a material. Now, the last thing we really need to discuss when we're talking about static stresses is the effect of stress concentrations, or stress risers, as some people call them. And essentially, it's just locations on, a engineering material that we're using in a structure that has some cross-sectional area change. Okay, so if we know the load conditions, let's say at the ends of a material, but between the material we have features here which are often necessary in shafts, for example, for notches, for seals, for ring clips, etc. Then although we know we will create a stress riser, it's often an engineering functional requirement, but we have to make sure that we understand that the effect of putting these features in these materials and the resulting stress that occurs. So anytime you have these sharp changes in cross-sectional geometry, you have these stress risers. This is an example of a photoelastic stress distribution, and it shows where we have these nice flows of stress here at the boundary conditions, but then here at these features we have these sharp gradients, and these sharp gradients are related to the stresses at these features. This is another image of a finite element stress distribution, and again we have these nice flow stresses, and you can see that the stress kind of flows around these features. Anytime we have these stress flows that have sharp gradients, another way of stating that is when these lines are really close together, then you have much higher stresses. Okay, and so we have these stress concentration factors. Okay, KT is the nomenclature that we use in this book. And what we do is we just find our nominal stresses on that cross-sectional feature, and then we multiply it by KT based upon information that we can get from handbook data or whatever. And we'll look at some of that here in a second. If we have shear stress concentration factors, we can use KTS times the nominal applied, or the nominal shear stress that's present in that material. This is an example here of a hole in a axially loaded member, and you can imagine many different machines that will have this type of feature. And the stress concentration in this case is related to these two parameters. A is half of the diameter, and then C is half of the diameter of the other axis if we have an elliptical shape. Okay. And what's interesting to note is if your C over A diameter here is, pretty high, then your stress intensity factor, your stress concentration factor, it's essentially 1. But when we get over ratios that are pretty low, the stress concentration can get up to 10 times that for an elliptical hole. So when we are doing engineering design and we are putting certain features in, this is these stress concentrations are not something that can be ignored and have to be taken account for. We're just going to walk through different tables here just to kind of get a sense and make sure that you can look this information up if you need it. So in this case, we don't have a hole or a fillet or anything. I mean, we don't have a hole or a groove, but we do have this change in cross-sectional geometry. All right, so if we have an applied moment here, and the nominal stress would be according to the flexural formula, which is the applied moment times the distance to the neutral axis to the outer fiber over the moment of inertia. We know the expression for this shape, which is given here. And then our max stress is just going to be our nominal stress times our stress concentration factor. So that's what we do for all these separate cases. And in this case, KT can be found from this equation or from this chart. And as you see, depending on the ratio here, we get all the way up to, 3-4 times the stresses just in this little change in geometry here. Now, what's important to note is when the radius is small here, in contrast to the diameter, then we have these higher stress values. All right, so we have these stress concentrations. This is taken from the appendix in your book, and we have to deal with them for every load case. All right, so this is an axial load with a step change in diameter. This is a torsional load with a step change in diameter. This is a bending load. This is for a shaft, obviously for a step change in diameter. This is if we have a groove in the middle of an axis under an axial load. And what's important and what I want you to see here is these values are, going up to 2.6, they're going up to 3, up to 3. And so we don't always want to, design something that can take 3 times the load, because then we'll end up spending more money and using more material. So we can't just say, oh, well, we'll design everything so that it's 3 times the stress on the end, that we don't have to worry about it. Instead, we need to really understand the effect of these cross-sectional geometries and then make sure that these stresses are accounted for in the entire design. And so another way of saying that is we have to practice the engineering rigor, if you would, to do a full analysis and really be aware of what's going on in our materials. In this case here, again, this is a shaft with a groove, applied moment, stresses go up to 3, and then we have these applied torque, the same thing, okay? And these are just different geometries. This is a shaft with a hole, all right? And you see that we can calculate these stress concentrations for those. These are plates with different features, step change in height, groove. This is a plate, thicker plate with a hole. And you can see that we have these equations that we can use to make sure that we're in a safe zone. The other option obviously is to do further analysis, finite element analysis. And in the case you have a design that's super complicated, what's often done is you do extensive testing to establish confidence if you have too much uncertainty. Now, a caveat to this is that ductile materials experience strain hardening, as we know. Okay, so if we go to some yield stress, we exceed that yield stress. There's some point in time, if we continue to increase the applied stress, that it will be harder and harder for that material to deform because we are strain hardening it, right? So to get any further deformation, we have to apply even increasing amounts of stress. Even for low carbon steel or aluminum alloy, they both experience that strain hardening, where more force is required to cause further elongation. And that's actually a desirable feature, and the reason why many things are made from ductile materials is that even if that material slightly locally yields, then that part of the material, remember, stress is at a point. Okay, so we're talking about points in the material or small areas of the material that have to yield. Well, if they yield, that material becomes harder to yield because of strain hardening. And then the rest of the cross section of the material has to yield for the part to fail. Okay, so stress concentrations in ductile materials don't represent the same threat as in brittle materials. This should say brittle materials. Okay, and that's because the local yielding reduces the effective cross-sectional area to deal with that stress. Okay, so that is a caveat for the ductile materials, and something that for a particular application is you need to keep in mind. Now, for brittle materials, that's not the case. Okay, stress risers, in brittle materials fracture, and they fracture because of crack propagation. And when you get a crack, to propagate it instantaneously can cause catastrophic failure. Okay, so the caveat for this is that when we get strength values for some materials, like then this crack propagation mechanism may already have been accounted for stress risers, okay, due to the nature of that material. And so the point is that, you know, your responsibility as a designer is to be aware of these things and then make sure that your design is safe, is not going to hurt anybody, and understand the difference between the failure modes for ductile and brittle materials and the effect of stress risers for materials. Now, this is only, what we've discussed is only for the static case. Under dynamic loading, even ductile materials will fail like brittle materials through crack propagation failure and fatigue failure, which we'll talk a lot about. Okay, so we have to modify these static load cases and stress concentration factors using the notch sensitivity parameter of that condition to correct for a fatigue stress concentration factor. Okay, and so we have to consider the dynamic loading, and in practice, more than 90% of machine components fail due to fatigue. Okay, and I know we focus a lot in the undergraduate program for, you know, statics and static failure and calculating the stresses, but it's not enough. Okay, so it's in this class where we talk about fatigue failure, and fatigue failure accounts for most machine component failures in all machines. Okay, and it's like $100 billion cost, you know, for the United States in like 1980s dollars. It's a big deal. Okay, so we need to be able to get our static design complete and make sure it's safe and doesn't fail. We also need to make sure that our dynamic design is also robust, and we have to consider fatigue, which we will be talking about soon. Now, there are some things that we can do to avoid stress concentrations, and that is by avoiding sharp changes in cross-sectional geometry. For example, this here, where we have a step change in shaft diameter, is totally undesirable because we have this sharp corner here, and we have these huge stress concentrations, and people will often see cracks, and cracks will start and propagate at these locations. All right, now instead, if you have the option, what you would like to do is you'd like to make these gradients less steep, or make these lines less packed in. And so you can almost imagine it, so this force flow concept is like, if you imagine these force lines flowing through, okay, if you go from here and now these lines have to flow through here, and you have the same number of lines, the only way for these lines, which are spread out, to go through this area, which is smaller, is for you to push all those lines together. And if they're all spread out at some location here, and then immediately they all got to get smashed into a smaller area here, then these lines have to have very sharp and steep changes. Okay, and this is this is called the force flow way of looking at things, and it's pretty simple. You just start at one end, make yourself some lines, and then when you have changes in area, all those same lines have to make it into there, and you can almost just imagine how it flows. And anytime we have these sharp changes here, so we have these high stress concentrations. One way to get rid of that or mitigate that effect is to provide the largest transition ratio as possible. Okay, so we can do that. And you can just see here the difference between the sharp edge and an edge with a larger radius. Okay, so it's a much smoother transition. So we have much smaller stress concentrations, and that's shown in those tables that we just looked at. Okay, so instead of this, never do this if you can avoid it. There's other ways you can do that. You can put a relief, okay, a reduction radius in the back side. For example, if you have to have a shaft and a bearing, you can change that notch to the other side. And I know that we have less material than we have in this case, but we have to deal with the cross-sectional area there and make sure that the design is still safe, but we've reduced those stress flows considerably. I mean, those stress gradients. Or we can add some washer or whatever so that we can have some condition that's more like this. Okay, so when you're designing, don't design without considering stress concentrations. All right, so that brings us to another concept of buckling. Okay, so when we have compressive axial loads, let me just show you a picture such as this. All right, the load is almost never in the middle. Okay, and I mean, just because you know, in practice, it's never going to be perfectly in the middle. And if we have a load here and a load there, and one of them is not perfectly in the middle, then we're gonna have to have a moment that reacts that offset load, and that moment is going to further cause that the member to want to bend. Okay, so we have to consider buckling when we have long rods or intermediate columns or slender rods. We have to consider those, and these show up all over in design. Okay, and this is a failure mode. It's a compression failure mode that's not associated with the material deforming necessarily. It has to do with the material just not being able to hold its shape under that load. Okay, we have a difference here between what we call short, intermediate, or long columns. Short columns fail in compression. Okay, and that means you just have enough material and it's short enough that you can, when you exceed the load, you just smash the material. Okay, you just exceed the compressive yield strength. When you get into a little bit longer columns, which we call intermediate or long columns, they'll fail by buckling at compressive stresses that are much lower than those for compressive failure. Okay, so we call the buckling a buckling failure. But to understand buckling, we need to know what the critical load is, and then we try not to exceed that critical load. All right, so short for our purposes, it will be a column which has a slenderness ratio of less than 10. And slenderness ratio, SR, is just the length of that column over the radius of gyration. And the radius of gyration is equal to the square root of the smallest second moment of area of the cross-section about the neutral axis divided by the cross-sectional area. Sometimes this is called the gyradius, okay? But the radius of gyration is the term. Okay, and it's the radial distance to a point whose moment of inertia is the same as the body if the mass was concentrated at that point. Okay, so it's the radial distance to a point whose moment of inertia is the same as the body if the mass was concentrated at the point. So you can almost think of it as if you took all the mass for the object and put it out at some radius, that's the radius of gyration for that material. Okay, now what we need to do is look at, well, how do we find that critical load? All right, so if we have this case here and we cut the cross section and we say the sum of forces are 0, the sum of moments are 0, we get that the moment minus the resistant load is equal to 0, or that the moment is equal to the force times the deflect distance y, and the distance y here is the offset in these two forces, okay, that they're here. Now, for small deflections of a beam, we can use the beam deflection equations. This is what we saw earlier when we looked at the beam deflection equations. We found the relationship, we derived this relationship actually for the slope of the beam and the applied moment. And we know that the applied moment is the second derivative of the deflection times EI. So if we divide the applied moment by EI, we get an expression for the second derivative of the deflection of that beam. Now, if we combine these two equations, we put PI in for M, so we get the PI over EI, and then we can subtract that from the other side. then we get we get a second order differential equation, right? So if we have y double dot plus p over ei y dot's equal to 0. And that's just, your second order differential equation, which has the general solution that we know quite well for this characteristic equation, where we have y is equal to c1 sine of the second coefficient here plus c2 cosine of the square root of the second coefficient, just like we see in calculus. All right. Now, C1 or C2, so we have to have two initial conditions. Okay, so it would be y and y prime. Y would be the deflection, y prime would be the slope. Okay, and so what we can do is we can look at the different, we'll come back to this, but we can look at the different boundary conditions. So if you see here for these conditions, the deflection y is going to be 0 here and 0 here if it's kept in line. If it's pinned, 0, 0. This case, 0, not 0. This case, the deflection at x equals 0, and x equals y is 0 and 0. Okay, so if we have that at y equals 0, at x equals 0, and we're saying that this is our x coordinate, so we're saying here y is 0, here y is 0. Those are our boundary conditions, so then we can find these coefficients. So then we get that C2 is equal to 0, so we don't worry about this guy. And then we have to worry about this guy. All right. And so if we find this guy for that initial condition, say y of 0 at x is 0, then we get this expression. So we need to find C1, and C1 is only going to be true, okay, if it's not 0, then we got to find the other places where it's true. Well, it is such that this equation is equal to 0 every time that it's equal to n pi, right? So if we have n pi, it's C1 times sine of n pi, where n is any number, right? It's 0. It's always 0, right? So then that allows us to use this equation here, and we make n equal 1. We just take the first case for the first critical load, and we can solve for p. Okay, so then that critical load p is really that solution. It comes from the solution of this second order differential equation for this deflection here. Okay, so then this critical load here. All right, so, and it may not be clear why we call this the critical load, so let me just come back here for a second and highlight that. The critical load is the load that is equal to a bending moment for some deflection y. What happens is when this is true at some deflection y, when it equals this bending moment, then this bending moment causes it to increase its deflection. Okay, so it's almost like a positive feedback, which makes the system unstable. Okay, so that's why we have to find that P that is equal to that, and it comes from solving for this deflection here, where this is true. Okay, so it may not have been obvious there when I explained it, but what we're really finding is we're solving for y, but our solution for y allows us to find for the P that causes that y, and then we get this expression down here for that critical load. Now, a couple things to remember. If the slenderness ratio, right, which we defined as as the length of the column over the radius of gyration, which we can calculate from what we know about the geometry. Okay, if it's less than 10, then we can just use the compressive stresses, just the load over the cross-sectional area, because it's short and it'll fail in compression. And what's interesting to note here is that the strength of material doesn't show up here. Okay, so you're not going to help yourself by getting a beefier, like a harder material or whatever, necessarily, especially if they have the same Young's modulus. Okay, so the strength of material doesn't come in here, so don't imagine you can put a stronger material here and have less susceptibility to buckling. Okay, that would be pretty naive, because that's not the mechanism that dominates this buckling phenomenon. It has to do with the material stiffness, Young's modulus and the geometry factors. Now, what's useful is for us to express this critical load in terms of the slenderness ratio. And we said earlier that the radius of gyration is the square root of I over A, so we can solve for I. I is AK squared. And so we can calculate the critical load from the equation we have in the previous slide. And instead of having L squared here, we just can replace it with we can replace I here with this AK squared. And I had to pause the video there and fix my algebra. So if we put I is equal to AK squared, we can put AK squared in for I. We put A, and we can bring that K squared down here. So then we get pi EA over L over K squared, and that's the same. That's the slenderness ratio. So we can express the critical load in terms of the slenderness ratio for a rod. Now, if we divide both sides by the area, then we can get the critical load over the area, and we can represent this critical load in terms of the stress. Okay, units of stress. If that's more useful. And then which can represent the strength of the column rather than the material. It's the stress that particular column can handle due to that load. Okay, it's the strength of the column, not the strength of the material. Okay, if we represent it like that. Now, fortunately, some people have helped us out, and they have found different boundary conditions for different situations, so we can calculate the slenderness ratio in terms of the effective length over the radius of gyration. All right, and those effective lengths are given here in this table. The American Institute of Steel Construction gives these recommended values. For our purposes, we say that, well, these are even more conservative, so why don't we just use these? This is recommended by Norton in the book based upon the different boundary conditions. So we can calculate our slenderness ratio based upon these boundary conditions, which cover most loading conditions here. Now, for this fixed free loading condition, the effective length of that rod is 2.4 times the length. Okay, so this is, for the rest of these conservative values, is to make the effective length 1, but in this case, fixed free case, we want to make it 2.4 times the length. Okay. Now, we have that theory, we have these critical loads. Unfortunately, in practice, these critical loads don't work for what are called intermediate beams. Okay, so at half the compressive yield strength, we have this point D where there's this difference between the data and what is predicted by the Euler line. So this analysis is from the Euler analysis. That's what we just did. Okay, so Johnson augmented this theory by fitting this line here, this black line from A to D, to the experimental data, because he found that if you were in this region, you actually had failure. So as long as we stay in these safe regions, which we can separate into this Johnson region in gray, and this Euler region here in this reddish pinkish color, then we're okay. So apologize if the video here is a little bit cut off. I had to stop my video there for a minute. So what we were talking about is these intermediate columns between sort of the shorter and longer columns. Based upon the theory that we just did of running through this process. This is the Euler column approach, and the Euler column approach predicts this curve here that's red. Okay, but in reality, there's this area here where the columns have shown empirically to fail. And so based upon the compressive yield strength for that material, Johnson modified this Euler curve with this Johnson region here that starts at point D. And point D is at half the compressive yield strength. Okay, so if your slenderness ratio is less than the slenderness ratio here, this is the SRD, this is the slenderness ratio at point D, and point D is at half the compressive stress for this curve, and there's different curves for different effective lengths that we'll show here in a second. But the point is, once you calculate your slenderness ratio, you need to know if you can use the Euler region or you can use the Johnson region. So if it's less, if the slenderness ratio that you calculate is less than the slenderness ratio at D, okay, then you need to use the Johnson portion of the graph because you're here in this Johnson region, okay? So you can use this expression here, okay, to make sure that you're below that line. All right, now to find your critical load needs to be below that line. All right, so if you're over here in the Euler region, you can use this expression over here that we derived from the Euler theory for the beam deflection. These are the failure lines for the different end conditions that we have. Okay, so this comes from here. So we have the different effective lengths. All right, so depending on the effective length that you're going to use for your end condition, then this point here is mapped out onto these for these different ratios, and you need to stay below these lines, okay, for your critical load. All right, so that's how we deal with columns. That's how we do the analysis. We're not gonna have you do any assignments related to these, but it's important to note that we also have eccentric columns that show up a lot in structural elements. And in this case, it's a little bit more involved because we have to include the eccentricity of the column, and we do that through this equation. You can read more about this in your book. And what you'll see here, down here on the x-axis, are different numbers for different materials. Okay, so this is for steel and aluminum. And so if you need to convert this for other materials, you can actually do that based upon the Young's modulus for their slenderness ratios of one to the other by using this equation. Like I said, this is beyond the scope of what I'm going to hold you accountable for, but eccentric columns do show up, and there is an analysis approach in the book that you can use. Now, the last thing we need to discuss for completeness, which shows up in some applications, is to do the analysis for thick-walled cylinders. Okay, so if we have a cylinder here where there's some inside pressure and some outside pressure, we can calculate that. This is for a thick-walled cylinder. For a thick-walled cylinder, we can look at the stresses, the stress difference, and it turns out that the stress is actually a function of the radius. Okay, so we see this is the radius here. So this is the tangential stress, and you see that it's greatest here in the inner wall and then goes down. And then we have an expression here for the radial stress, which is also the greatest here and then goes down. And this is assuming that the inside pressure is higher than the outside pressure. And then we have an axial stress if these ends are capped. Okay, this is just the stress that tries to pull that material apart. Okay, so we have these three stresses that can act on stresses in cylinders. These are due to Lamb's equation. If we have thin wall cylinders, which is what we use for pressure vessels, to avoid failure, explosion through the surface, we need to make sure that the inner pressure does not exceed the hoop stress or the longitudinal stress. The hoop stress comes from the stress balance of the pressure acting on this area, this projected area. So if we take that pressure and we say that it's picked up by all of this area here at the top of the bottom, and we do the force balance, we get this expression here, which is just that stress times the area, which is that force that's here at the top and the bottom, minus the pressure that's projected on this area, which is twice the radius, times the thickness, that's that area. Then we can just do the force balance. When we do that, we find that the hoop stress is this, which is just PR over T, where P is the inner pressure times the radius over the thickness. The stress on the ends, if the ends are capped, in this case, we just again do the force balance and stresses, and that's PR over 2T. Okay, so these are what we use to find the effective stresses due to pressure in thin-walled cylinders. If we have spherical vessels, then we have just a little bit different geometry, and the pressure drops from PR over T to PR over 2T. Okay, so if we use a spherical vessel, we can the stress due to the same pressure is half. Okay, then the hoop stress here in this case, PR over T. All right, so that's all we have, and we'll do a couple examples for the columns to show you how to use the slenderness ratio.